Alright, we're going to look at number 16 to start applying all these properties and all these formulas that we have been learning about summation notation. And I would like you to think back to last year and how we did take a test on this at the end of the year. And what I don't want to see happen is last year I still had people, even though we have these properties and these formulas, people would still be writing out something like this: 2 times 1 minus 3, alright, and then plus 2, and they would be doing this all the way up until 2 times 15 minus 3, and then they would have to add all of those up and finally get an answer. I don't want to see that happen this year. Alright, so I'm going to start using the properties first, and then we'll switch to the formulas. But one of those properties stated that if you had any kind of many terms being added or subtracted, so what you can do is break it up. So I'm going to rewrite it. And then also here we have a constant, so I'm going to rewrite it once again. So we've gotten it to a point where we've used that sum and difference rule, and then we've also used the constant rule. And what I'm going to switch us back to is this right now. And what we can use, actually, I just went back and I transferred from this page onto this page those formulas. What I want you to see right here is that I have, whoops, didn't mean that, this piece right here would match the type of pattern where I'm trying to add up terms of just some sort of singular variable. So what I would have is this is all equal to 2 times, and I'm going to use this right here. And instead of having this summation form in, I'm going to rewrite it as the formula that it would equal. So I have 15 terms all in all. From 1 to 15 I have 15 terms, so I'm going to be writing 15 squared plus 15 all over 2, and then minus, this right here is going to be matching this type of sigma notation where you have some sort of constant and you're trying to add up that many terms from 1 to n. So in this case from 1 to 15, so we are going to have 3 times however many terms we have, which in this case is 15. So now what this becomes a matter of doing is on your calculator these actually cancel each other out. So I'm just going to have to calculate 15 squared plus 15 minus 3 times 15. When you do this, your answer is 195 on your calculator. Okay, so done. You can see how that would be a lot quicker than using, you're using sigma notation to its fullest there by expanding it all out, but that would take a very long time. We're also going to look at number 43 now. 43 is almost like this, except for we're going to be calculating a limit. And this one is very complex, so hopefully if you get this one you'll be able to get all the other summation problems. So what I would like you to first notice is if you were to actually try to expand this out, we're going to be trying to find the limit of this summation. And the problem with that is you are going to first have to calculate this all out. Get it into the most simplified type of form that you can get it, so that eventually we're going to be using something that we learned in chapter 5.6 on finding the limits towards infinity. So if you were to try to expand this out, this is what it would start to look at. I do want you to note that this is a constant. This index letter is I, and what we would be plugging in as we go from term to term, we're adding each one of those terms, is you would be plugging in for that I. So if you look over here, here's that index number, here's that index number, and here's just some sort of constant that we don't really know. And if you were trying to avoid formulas and properties altogether, there really would be no end to this. So what we're going to have to really do is you can't just try to expand it out in this way. You're going to really have to use the summation properties. So for now, we're going to get this cleared up, and then eventually we're going to be applying the limit. So you're going to see me writing this, but I'm going to kind of be ignoring it for now. We'll address it at the very end of this. So the first thing that I do want to say is I'm going to pull this out. This is a constant. So I'm going to pull that out as 1 over n cubed. And I know it's confusing because it has that variable n there, But like I said, it's not affected by this index as we go from term to term. So it's just going to be remaining constant as we go add this term plus this term plus this term and so on. So I am going to put in parentheses then the sum I equals 1 all the way up to n. And then I am also going to expand this out at the same time. I squared minus 2n and then plus 1. And this is just me foiling the I minus 1 squared. Okay, so the next thing that I am going to do is I'm going to kind of, first of all, apply that one formula, or I'm sorry, apply that one property that you can add each one of these. I'm trying to find the sum of this polynomial, but I'm going to just find it term by term, so the limit. And then I'm also going to apply that constant rule right there. Alright, and then just so I don't forget, this 1 over n cubed does apply to all of these, so I'm going to redistribute that in right now. So we're finding the limit as n approaches infinity, and I'm going to just distribute this back into each one of these individualized sigmas or sums. So we have oops, this should be an I. I'm sorry. This is an I. Alright, now that I have that, I'm still looking at the limit here. Eventually I'll evaluate the limit. But here, now that I have it in these forms, I am going to be rewriting these sigma notations. So this whole thing right here is going to be rewritten. I'm going to take the sigma out but rewrite it in the formula that it's equal to. So you'll see that here I have the sum of our index variable being squared. Here it is right here. I have the sum of our index variable being squared, and then it's all brought up to the end. So we don't have a 15 or some sort of specified number like we did the last time. So here we're just going to have to keep n. This whole thing is going to be going in for this whole thing. So what I'm going to be getting here is the limit as n approaches infinity of 1 over n cubed, and then this whole thing times 2n cubed plus 3n squared plus n all over 6. Okay. And then right here I am going to simplify this piece, but we have a minus, we have a minus, and then 2 times 1 over n cubed is just 2 over n cubed. And then here we have the summation of just our single variable, our index variable. So here we have that formula is equal to just however many numbers that we are going up to. In this case it's just n, so we have to keep that n. Okay, and then we have plus, and then our constant, so it's just 1 times n. Oh, I'm sorry, don't forget here though we have a 1 over n cubed. This had to distribute all the way, so it's going to be 1 over n cubed times 1 times n. Alright, now that we have that, I am going to go ahead and start to simplify things. So this is going to all be equal to, when I multiply this back in, I'm going to be multiplying 6 times n cubed, and some of these are going to reduce. So we have the limit as n approaches infinity of 2n cubed plus 3n squared plus n all over 6n cubed, and then minus, and then here these 2's cancel each other out, so I am going to be getting n squared plus n all over n cubed plus, and right here I have n over n cubed. So now here is, think back to limits and formulas, or I'm sorry, properties of limits. If you have a limit of many terms like we have right here, you can also take that limit and to a point distribute it to each one. So here I'm going to rewrite this as the limit as n approaches infinity of 2n cubed plus 3n squared plus n all over 6n cubed minus the limit as n approaches infinity of n squared plus n all over n cubed, and then plus the limit as n approaches infinity of n over n cubed. And what we're going to want to do is, just like in 5.6 now, this is 5.6, we're going to be calculating these limits at infinity. And what I am going to do is, notice right here, my highest degree on the bottom is n cubed. So what I'm going to do is divide everything by n cubed. Okay, so that I'm eventually going to rewrite. Down here it's the same thing, n cubed. So I'm going to divide everything by n cubed. And then here, divide everything by n cubed as well. Oops. Sorry, I ran out of room here. So when we rewrite this, what we'll have is the limit as n approaches infinity of 2 plus 3 over n plus 1 over n squared all over 6, and then minus the limit as n approaches infinity of here, it's going to just be 1 over n plus 1 over n squared. That looks like a 3, but it's a 2. And then we have over 1. And then plus, right here, these are also going to cancel each other out. We're going to get, the limit as n approaches infinity of 1 over n squared all over just 1. And here, these are going to go to 0. When we calculate the limit of some sort of constant over our variable n, and this is going towards infinity, if this were going towards an infinity or infinity squared, this whole thing starts to go to 0. So that first term is going to be 2 over 6 minus this right here, it's going to be 0 plus 0 over 1, so just 0. And then plus, and then right here we just get 0 as well. So 2/3, or in other words, this is equal to, all equal to 1/3. Alright, so believe it or not, when you look at this, and we're studying the summation of this sequence, and you are adding up all of these terms, what's going to happen as we let n go towards infinity, as we just keep adding up more terms and more terms and more terms, it gets to this point though where the term value is going to become so small that you're really not adding anything up. So this is what we called last year converging sequence, and what happens is we're going to get an ability to add up the sums, and it's going to be 1/3.